Welcome to the course module, Introduction to Similar Exposure Groups. My name is Rachel Jones, and I'm a professor at the University of California, Los Angeles Fielding School of Public Health. The learning objectives for this module are: 1. Explain the concept of a similar exposure group. 2. Explain the role of variability in similar exposure groups. 3. Define and develop an exposure profile. 4. Explain the role of similar exposure groups in measurement strategies. In this part of the module, titled Defining Exposure Profiles, Objective 3 will be addressed. Two common types of probability distributions are the normal distribution and the log normal distribution. The normal distribution is characterized as bell-shaped. Figure 1 shows a histogram of exposure data that are normally distributed in the gray bars, where the red line shows the idealized normal distribution for these data. The vertical blue line denotes the mean. The normal distribution is symmetric around the mean, which means there are equal numbers of observations on either side of the mean. The mean corresponds to the most likely value, indicated by the peak of the red line. It also corresponds to the median value. A normal distribution is defined by two parameters: the mean and the standard deviation. The log normal distribution is right skewed, which means that there is a small probability of observing very high values. The log normal distribution is also not symmetric around the mean. Figure 2 shows a histogram of a log normal probability distribution in the gray bars, where the red line shows the idealized log normal distribution. The mean, indicated as a blue line, is not in the center. In fact, the mean value is to the right of the most likely value, denoted by the peak of the red line. This is different than what we saw in Figure 1 with the normal distribution. Another important feature of the log normal distribution is that the values of the data are only positive. Even when data are log normally distributed, it's possible to calculate a mean and a standard deviation. It's more appropriate, however, to describe a log normal distribution using the geometric mean, denoted GM, and geometric standard deviation, denoted GSD. The log normal distribution is related to the normal distribution. For log normally distributed data, the logarithm of the data is normally distributed. Years of exposure monitoring, data collection, and analysis have demonstrated that the variability in exposure monitoring results in the workplace are best represented by a log normal distribution. Two characteristics of exposure monitoring data that align with the properties of the log normal distribution are that values are always positive and very large values sometimes occur. In statistical terms, the second characteristic means that the exposure monitoring data and the log normal distribution are right skewed, as we saw in Figure 2 on the previous slide. To guide our discussion of exposure profiles, we are going to use a data set collected by Michael Wilson and colleagues about the exposures of automotive mechanics to organic vapors. The work was published in the Journal of Occupational and Environmental Hygiene in 2007 on pages 301 to 310 in Volume 4, Issue 5. A portion of the data is shown in Table 1, and it includes personal breathing zone samples collected during brake inspections involving the use of aerosol solvent products. 3 chemicals, hexane, acetone, and toluene, were analyzed in each sample. A total of 13 personal exposure measurements were collected from 9 workers in 3 shops, denoted A, B, and C. One of the first things hygienists do with exposure monitoring data is to look at it graphically, such as with a histogram. This can give us information about whether the data are log normally distributed, among other information. Figure 3 shows histograms of the hexane, acetone, and toluene exposure concentration data from Table 1. As we can see, these histograms are neither symmetric nor bell-shaped. They are, however, kind of right skewed. This means that most samples have relatively low concentrations, and the bars on the left side of the graphs are tall. But a few samples have higher concentrations, and the bars on the right side of the graphs are lower. These graphs are typical of exposure measurement data. While 13 samples is a good size exposure data set, it is small from a statistical perspective and can yield histograms like those shown in Figure 3 that don't look like what you see in statistical textbooks. I'm going to use a little bit of mathematical notation here to show how to calculate log normal distribution parameters. This is discussed in more detail in other modules, so I will be brief. Let capital X denote a set of measured values, x1, x2, x3, all the way up to xn, where n is the number of measurements. And let capital Y equal the logarithm of capital X and denote the set of the logarithm of the measured values. The mathematical expressions for the two key parameters in the log normal distribution, the geometric mean and the geometric standard deviation, are shown below, along with the results calculated for the hexane data. Now, if you don't feel like doing these kinds of calculations by your hand or with a calculator, there are online tools that you can use to do the calculations. One of these tools is called IHStat. The software IHStat can be used to calculate log normal distribution parameters, including geometric means and geometric standard deviations. The program is set up in an Excel spreadsheet and is available for free download from AIHA. The link to access IHStat is shown below at the bottom of this slide. Figure 4 shows a portion of the IHStat interface. The user inputs the exposure measurement data, denoted sample data, in IHStat, and can input an occupational exposure limit. With these inputs, the IHStat software will provide descriptive statistics in addition to log normal distributions and probability plots. Here I show how to input the hexane data from Table 1 into IHStat in Figure 5. For the OEL, I used the NIEHS recommended exposure limit of 180 milligrams per cubic meter hexane. The measured hexane concentrations from Table 1 were entered under the sample data column. After entering the data on the left of the red line, descriptive statistics and other information are calculated and displayed on the right of the red line. Looking to the right of the red line, we can see that IHStat has calculated the geometric mean of the hexane data to be 31.89 milligrams per cubic meter and the geometric standard deviation to be 2.153. The software also reported that 0% of the measured hexane values are above the OEL, which makes sense because the maximum concentration measured was 100 milligrams per cubic meter, which is lower than the OEL. The hygienist's goal is to ensure that the vast majority of exposures are less than the OEL. The 95th percentile of the log normal distribution is a critical value in making this decision. The 95th percentile indicates the value that 95% of exposures are less than or equal to, and 5% of the exposures are greater than the 95th percentile. In this example, the 95th percentile is 112.620 milligrams per cubic meter of hexane. The upper tolerance limit, or UTL, is the upper limit of the 95% confidence interval around the 95th percentile and is denoted the UTL sub 95%, 95%. IHStat calculated this value as 247.25 milligrams per cubic meter hexane, which means that there is some chance that the 95th percentile of the true distribution of exposures may exceed the OEL of 180 milligrams per cubic meter hexane. Here in this module, my goal is to illustrate the tool IHStat, and other modules explain the meaning and interpretation of these statistics in more detail. In Figure 6, you can see the histogram of the hexane exposure data calculated by IHStat. The blue bars depict the observed frequency of measured concentrations. The yellow line shows the fitted or idealized log normal distribution curve using the calculated geometric mean and geometric standard deviation. IHStat also produces log probability plots. Figure 7 shows the log probability plot for the hexane exposure data from Table 1. The data are the blue squares. The straight green line shows the ideal log normal distribution. When the blue squares are close to the straight green line, it means the data likely follow a log normal distribution. The 95th percentile of the exposure distribution can be identified from this plot, as shown by the red dashed arrows. The 95th percentile is approximately 150 milligrams per cubic meter hexane. The 50th percentile of the distribution, or median, can be read from the plot by the solid red arrows and is approximately 35 milligrams per cubic meter hexane. Referring to the example in Table 1, you can calculate the geometric mean, geometric standard deviation, and 95th percentile of each chemical using IHStat, as described in previous slides. These values are shown in Table 2, and they are the key statistics to define exposure profiles for hexane, acetone, and toluene of workers doing brake inspection tasks. Exposure profiles are developed using multiple measurements to account for variability over time, tasks, locations, or workers. Collecting exposure measurements on multiple days and among multiple workers helps to ensure the data are sufficient to define the exposure profile and represent the full range of exposures that can occur within the SEG. As in this example, it is common for workers to be simultaneously exposed to multiple agents. Therefore, exposure profiles are developed with consideration of all hazardous agents that workers potentially are exposed to. In this example, we considered 3 agents: hexane, acetone, and toluene. If workers in an SEG perform multiple tasks, exposure assessment needs to account for all tasks over the work shift. The hygienist can address this challenge by combining exposure data from different tasks to estimate representative 8-hour time-weighted average exposures. Or the hygienist can measure exposures for full 8-hour shifts during which workers perform the different tasks. To conclude, exposure profiles provide statistical descriptions of exposures encountered by all of the workers in an SEG. The exposure profile is typically characterized by a log normal distribution. An exposure profile requires exposure data that represent the full range of exposures and exposure determinants encountered by workers. That means that an exposure profile is only as robust and representative of workers' exposures as the sampling strategy used to collect the data that underpins the exposure profile.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.